September 14, 1943. Dawn breaks over RAF Molesworth in Cambridgeshire. Lieutenant Colonel Arthur Vandenberg stands beside the twisted wreckage of a B-17 bomber, its fuel tank split open like torn metal flowers. No flak damage, no bullet holes. The aircraft simply exploded during a routine refueling operation at 18,000 feet. Vandenberg is an engineering officer with the 8th Air Force, responsible for keeping America's bomber fleet operational over occupied Europe. This is the third unexplained mid-air explosion in 2 weeks. Vandenberg kneels beside a scorched rubber hose still attached to the wreckage. The metal coupling shows no structural failure. The fuel was pure. Weather conditions were clear. Yet 7 men died in an instant, their bomber disintegrating without warning. He runs his finger along the hose interior and feels the residue of something he cannot yet name. The investigation begins here, in the cold English morning, with a man who refuses to accept mystery as explanation. The problem is urgent. Allied strategic bombing depends on mid-air refueling to reach targets deep in German territory. Without it, bombers cannot strike the factories producing tanks, aircraft, and munitions that sustain the Nazi war machine. But crews are growing afraid. Pilots report seeing bright flashes inside fuel tanks during hookup. Tanker operators describe sparks jumping from metal to metal. Some refuse to conduct operations above 15,000 feet. Vandenberg has 2 weeks to find the cause before the Air Force grounds the entire refueling program. He begins with the physics. At high altitude, the air is thin and extremely dry. Temperatures drop to 20 degrees below 0 Fahrenheit. Under these conditions, friction between materials generates static electricity with nowhere to dissipate. Vandenberg requests test equipment from the engineering depot at Burtonwood. He needs to measure electrical charges in conditions that simulate operational altitude. The equipment arrives on September 17th. He sets up a makeshift laboratory in a hangar at Molesworth, using compressed air to simulate altitude and refrigeration units to replicate temperature. The first tests confirm his suspicion. When rubber hoses are dragged across metal couplings in cold, dry conditions, they generate electrical charges exceeding 10,000 volts. A single spark in a fuel-rich environment is enough to trigger catastrophic explosion. The rubber hoses used throughout the 8th Air Force Fleet are perfect insulators. They trap charge with no path to ground. Every refueling operation at high altitude is a potential detonation waiting for the wrong moment of contact. Vandenberg documents everything. He photographs the test setup. He records voltage measurements at different temperatures and altitudes. He calculates the threshold at which static discharge becomes lethal in the presence of aviation fuel vapor. His report fills 23 pages of technical analysis, but the conclusion is simple. The current refueling system is fundamentally unsafe at operational altitude. On September 22nd, he presents his findings to Brigadier General Frederick Castle, commander of the 4th Bombardment Wing. Castle reads the report in silence, then asks the only question that matters. Can it be fixed? Vandenberg proposes a 3-part solution. First, replace the rubber hose linings with conductive material that allows static charge to flow rather than accumulate. Second, install grounding cable assemblies that connect every metal component in the refueling system to the aircraft frame, creating a continuous path for electrical discharge. Third, implement mandatory protocols requiring crews to bond all equipment before fuel transfer begins. The solution is comprehensive but expensive. It requires retrofitting hundreds of aircraft and retraining thousands of personnel. Castle approves it immediately. The alternative is losing bombers faster than factories can build them. Implementation begins on September 28th. Vandenberg works with procurement officers to source conductive hose material. Standard rubber will not work. He needs hoses with embedded carbon particles that conduct electricity while maintaining fuel resistance. The material exists but is rare. Most production goes to ground-based applications. Vandenberg argues that aerial refueling is a strategic priority. He secures enough material to retrofit 50 tanker aircraft by mid-October, with more arriving weekly. The grounding cables present a different challenge. Each assembly must be custom-fitted to specific aircraft types. B-17s require different configurations than B-24s. Tanker aircraft need additional grounding points to handle the fuel transfer equipment. Vandenberg creates detailed installation diagrams for each aircraft model. He trains maintenance crews at Molesworth, then sends them to other bases across England to spread the knowledge. By early October, teams are working around the clock to install grounding systems on every aircraft in the refueling fleet. The human element is harder to fix than the hardware. Refueling crews have operated the same way for months. They are accustomed to quick hookups and rapid fuel transfer. Vandenberg's protocols slow everything down. Before each operation, crews must now connect grounding cables between tanker and receiver. They must verify electrical continuity with test equipment. They must wait 30 seconds after connection before opening fuel valves. Some crews resist. They argue that the delays expose them to enemy fighters. Vandenberg is unmoved. He shows them photographs of the wreckage at Molesworth. He explains that static electricity kills faster than any German pilot. On October 12th, the first fully modified tanker conducts operations over the North Sea. The crew follows Vandenberg's protocols exactly. They connect grounding cables. They verify continuity. They wait before opening valves. The refueling proceeds without incident. No sparks, no flashes, no explosion. The bomber receives full fuel load and continues to its target in the Ruhr Valley. Vandenberg monitors the operation from Molesworth by radio. When the tanker returns safely, he allows himself a moment of satisfaction. The system works. Now it must be proven across hundreds of aircraft and thousands of operations. The data begins to accumulate through late October and November. Before Vandenberg's modifications, the 8th Air Force recorded an average of 4 electrostatic explosions per week during refueling operations. After implementation, the rate drops to less than 1 per month. The reduction is 89%. Vandenberg tracks every operation, every incident, every near miss. He adjusts protocols based on field reports. When crews report difficulty connecting grounding cables in turbulence, he redesigns the cable clips for easier attachment. When maintenance teams struggle with installation time, he streamlines the process. The system evolves through constant refinement. By December 1943, the entire 8th Air Force refueling fleet operates under Vandenberg's protocols. The fear that gripped crews in September has dissipated. Pilots no longer report sparks in fuel tanks. Tanker operators conduct high-altitude operations without hesitation. The bombing campaign against Germany intensifies. Long-range missions that were impossible in summer become routine in winter. B-17s strike aircraft factories in Regensburg. B-24s hit oil refineries in Ploesti. The sustained pressure on German industry begins to show results. Production rates decline. Supply lines falter. The Third Reich's capacity to wage war diminishes month by month. Vandenberg's contribution remains largely invisible. His name does not appear in mission reports or operational summaries. He receives no medal, no public recognition. But the pilots and crews know. They understand that someone solved the problem that was killing them. In the ready rooms and mess halls of English air bases, his protocols become standard practice. New crews learn the grounding procedures as fundamental elements of refueling operations. The knowledge spreads beyond the 8th Air Force. By early 1944, every Allied air unit conducting mid-air refueling adopts Vandenberg's system. The technical innovation extends beyond immediate application. Vandenberg's research into static electricity at high altitude influences post-war aviation design. Aircraft manufacturers begin incorporating conductive materials and grounding systems as standard features. The principles he established become foundational elements of fuel system safety. His documentation serves as reference material for engineering students and military planners for decades. The problem he solved in a cold English hangar shapes the development of aerial refueling technology through the jet age and beyond. The strategic impact is measurable. In 1943, before Vandenberg's modifications, the 8th Air Force flew an average of 1,200 bomber sorties per month against German targets. By mid-1944, with reliable high-altitude refueling, that number exceeds 4,000 sorties per month. The increased operational tempo devastates German industrial capacity. Tank production falls by 40%. Aircraft production declines by 35%. Oil refining capacity drops by 60%. The systematic destruction of Germany's war-making ability shortens the conflict by months, perhaps years. Every mission enabled by safe refueling operations contributes to that outcome. Vandenberg continues his work through 1944 and into 1945. He monitors incident reports, refines protocols, trains new personnel. When problems emerge, he investigates and implements solutions. When the Air Force introduces new aircraft types, he develops grounding systems for them. His approach remains consistent. Systematic analysis, practical solutions, rigorous testing, continuous improvement. The methodology he applies to static electricity becomes a model for solving other technical challenges facing the bomber fleet. The war in Europe ends on May 8, 1945. By then, Vandenberg's refueling protocols have been in operation for 19 months without a single electrostatic explosion in properly equipped aircraft. The safety record stands as testament to engineering discipline applied under operational pressure. Thousands of aircrews owe their survival to modifications they never saw and a man they never met. The bombers that struck the final blows against Nazi Germany carried fuel transferred through systems designed in a Cambridgeshire hangar in autumn 1943. Vandenberg returns to civilian life in late 1945. He takes a position with an aircraft manufacturer in California, applying his expertise to commercial aviation. He never speaks publicly about his wartime work. The technical reports he wrote remain classified for decades. When they are finally released, historians recognize the significance of what he accomplished. A silent killer that threatened to ground the Allied bombing campaign was identified, understood, and eliminated through methodical engineering and systematic implementation. The wreckage at Molesworth was cleared away in September 1943. The hangar where Vandenberg conducted his tests was demolished in the 1960s. The air base itself closed in 1973, but the principles he established endure. Every modern aircraft that conducts aerial refueling incorporates grounding systems and conductive materials descended from his original design. Every crew that connects a refueling boom follows protocols rooted in his work. The problem he solved has not recurred in 80 years. Arthur Vandenberg died in 1982 at the age of 73. His obituary mentioned his service with the 8th Air Force, but provided no details. The men he saved never knew his name. The missions he enabled are recorded in official histories without reference to the technical foundation that made them possible. Yet his contribution remains embedded in the structure of modern military aviation, invisible but essential, a solution so complete that the problem it addressed has been forgotten. That is the nature of successful engineering. When it works perfectly, it disappears.